Welcome back, everyone. We are working our way through chapter 13, and we are covering the second to last section today, 13.6, which is titled Circular Functions, which is somewhat appropriate because it all comes back to the unit circle. We've been talking about the unit circle as we've gone through this chapter, adding on bits and pieces. We're really going to be using it, in 13.6 and 13.7. So, the first thing, and this is almost an aside, but you will sometimes see problems that ask questions phrased this way. We know that on the unit circle, the coordinates of a point on the circle are equivalent to the cosine and the sine value, because we know cosine is x over r and sine is y over r, but on the unit circle, what is the radius? It's just 1, which means cosine is just the x coordinate, sine is just the y coordinate. We know that. We've seen that and talked about that. So some problems will wrap this concept up and try to make it super confusing. And it doesn't need to be. And that's what I'm going to demonstrate just with this one example. It says, given an angle theta in standard position, if the point 2 root 2 over 3, comma, negative 1/3 lies on the terminal side and on the unit circle, find sine theta and cosine theta. What is that saying? That's saying that 2 root 2, and so that's 2.14, so almost 3. Almost 3 over 3, so almost 1 is the x, and negative 1/3 is the y. If this side is on the unit circle, if this point, what are sine and cosine? Well, all it's saying is, hey, remember, that's cosine. And the y value, the y coordinate is sine. So sine, I'll try to color code this, I'll make this blue. Sine, this type of question is just making sure you know that sine of theta is the y coordinate and that cosine of theta is the x coordinate. And there's nothing more to it. Don't overthink it. You know that on the unit circle, sine is the y, cosine is the x. So if you know those points, those coordinates, it's given to you, we're in business. So that's just a brief little prelude to this lesson. But here we go with the more interesting stuff. This is more what circular functions refers to. The graphs of sine of theta and cosine of theta are shown on the right-hand side of the screen. They're these oscillating waves, these waves that go up and down and up and down and up and down in that same pattern forever and ever. And this is something that's been really useful to us. We've actually used this fact to our advantage already in this chapter. You might not have realized it. So the first thing I want to do is show you how this works, why the graphs relate to the unit circle. Think about from 0 to 90 degrees, and we're going to start with sine. Sine is the y coordinate. The y coordinate starts at 0 and kind of follows this circle up to 1 when it gets to 90 degrees. That's that part of the graph right there. It starts at 0, the y coordinate does, and gets up to 1 at 90 degrees. Now, what about from 90 to 180? 90 to 180, it's going down from 1 to 0, which again is exactly what we see on the oscillating graph on the coordinate plane. What about from 180 to 270? It's going from 0 all the way down to negative 1. We're just talking the y coordinate, remember. We're going down to negative 1. And then from 270 to 360, we're making our way back up because we were at negative 1 in the y, but we're getting back to 0. We were at negative 1, we're getting back to 0 there. So I want to pause and just look at that graph and that circle and see if you can see the y values that come from the unit circle that generate this graph. Starting from 0 degrees, working our way to 360, we start 0 in the y, we go up to 1, we go down back to 0. We go down further to -1, up back to 0. And then what's going to happen? It's a circle. And so we know it's going to go up to 1. Again, that was kind of sloppy. I'm going to fix that. Up to 1. And down to 0. And it will continue this way forever. This is why this pattern never changes, is because the y coordinates just go from -1 to 1 in this circle, this unit circle that we never escape. Similarly, I'm not going to erase all the highlighters, but I am going to highlight the cosine graph. Cosine is x. So right here, I'll kind of scribble, from 0 to 90, we started our x at 1, and it worked its way back to 0. So it started at 1, worked its way back to 0. Then from 90 to 180, scribble, 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 scribble. We were at 0, and our x's went from 0 to -1. That's what's shown here on the graph, 0 to -1. But then in green, we were at -1 in the x-axis. We're working our way back to 0 by the time we get to 270. And sure enough, 270 to 360, we go from 0 to 1 in the x direction. And so again, I'm hoping you kind of see where that graph is coming from. It is not, I will admit, it is not imperative at this point in your math career that you 100% see where it's coming from. But it is helpful to understanding and realizing kind of what's going on here, why the graphs look this way. So these functions are known as periodic functions. A period is an amount of time, and these functions, it's said, they repeat periodically. So how often do they repeat? Well, what I like to do is find a very distinctive point, say right here, the top of a hill, and say, how long does it take us to work through one full cycle to get back to the top of the hill and then start that next cycle and next cycle? Well, 90 to 450 is 360 degrees. The period is 360 degrees because that's how long it takes for us to repeat. 360 degrees, that makes sense because that's our full circle, and we know that we repeat once we complete another revolution. So 360, I'm hoping, is making perfect sense. Similarly, we could do the same with cosine. I'm anticipating it to be 360. Maybe we go the valley this time. Maybe we say, okay, valley, we go up, we go down, and then we're getting ready to go back up again. So that's one full cycle. Sure enough, from 180 to 540, we've covered 360 degrees. So when you're asked what is the period of a function, that means how long does it take for us to complete one full cycle? Now these are on the unit circle, but let's look at one that's just, I made it up, I drew it. How long does it take for this periodic function to repeat? Maybe you choose a hill, maybe you choose a valley. Maybe you choose this, like, I don't know, I think it makes sense to choose something that is easy to see. So I'm going to choose the valley because it looks like it's about on 1. And it goes up and all this crazy stuff is happening, and then I get to the valley and it looks like it's about on 3. So what is the period here? It was 2 units to get one full cycle. We're going to say the period is 2. And we could have figured that out from peak to peak. It's like maybe 0.4-ish to 2.4-ish. So that also took 2 to repeat. We can figure it out with any distinctive point in the graph where we can tell, oh, we finished one cycle, we started another. So that's what a circular function looks like, a periodic function. Now, here's the cool thing, and the thing that we've actually been using already, whether you realized it or not. This means that sine of theta, the y value of theta, is exactly the same as sine of theta plus 360. We could go a full circle, we'll end up at the same point, it'll have the same y coordinate, the same sine value. We could even add 720. We could do 2 full circles and end up at that same point, or 3 full circles, or 4, or 10. We could add full circles, subtract full circles, and the sine values will remain the same. The cosine values will remain the same. The tan values will remain the same because the x's and y's remain the same. In radians, how do we add full circles or subtract them? Add another 2 pi, add another 2 pi. So 4 pi, 6 pi, 8 pi. Maybe subtract if we need to. But if we know the values on our unit circle really well, we can basically say what these trig values are for any angle just by adding or subtracting full circles. As I said, we've been doing this. Let's continue to do it. 750 is not on my unit circle. I know that my unit circle typically goes 0 to 360. So what I'm going to say is, okay, well, what if we subtracted a full circle? Because I don't know where 750 is, but if I subtract a full circle, it looks like 0, 9, oh, it's at 390. That's also not on my unit circle. So let's just subtract another 360. 30 degrees, that is on my unit circle. I know that 30 is right here, thereabouts. And that makes sense because 750 is 30 more than 720 degrees. If you recognize that value, so 2 full circles plus another 30. So if we end up there, I want to know the sine value, the y coordinate. It's my small side on a 30, 60, 90 triangle. And so sine of 750 is 1/2. 750 wasn't on my unit circle, but I know I can subtract circles, end up in the same place. It should be the same as sine of 30 degrees, which is 1/2. What about cosine of 19 pi over 4? Okay, so radians we're a little less comfortable with, familiar with, I would say, but I do know that to subtract a full circle, I can just subtract 8 pi over 4, because that's 2 pi, right? 8 pi over 4, 2 pi, common denominator, so 11 pi over 4. Great, still not on my unit circle, so I'm going to subtract another full circle, 8 pi over 4, gives us 3 pi over 4, and I do recognize that radian measurement. 3 pi over 4, remember 180 is 1 full pi, so 3/4 of the way there would be right about there. I'm looking for cosine. This is a 45, 45, 90 triangle. And so if you remember, the legs in our special right triangle root 2 over 2, but I'm going left, so it's negative. Negative root 2 over 2. What about tan of 765? Maybe we see right off the bat that we want to subtract 2 full circles. So I say 765, I could subtract 2 full circles and get to 45. Oh, I know exactly where that is on my unit circle. 45 is splitting right down the middle right here. And so it's a 45, 45, 90. I know those are the same. They're both going to be root 2 over 2. I know that tan is y over x. Root 2 over 2 over root 2 over 2. And what is anything over itself? Tan 765 equals 1. So this is the idea of circular functions, that we can just add or subtract full circles, and we can find these trig values for these big angles or these super small angles. If you notice that cosine 1 on the right, you'll probably have to add 1, 2, maybe 3 circles to get into a positive degree measurement that we recognize. That's what I want you to do. I want you to pause your video right here and try to work out those 3 problems on the right. What is sine of 40 pi over 3? What is cosine of negative 990? And what is tangent of 7 pi over 2? Try to pause it and work them out. I'm going to work them through and talk through them. So if you're confused, just stay on the line, and here we go. Sine of 40 pi over 3. 40 pi over 3. I know I need to subtract a full circle or 2 or 4 or 10. A full circle would be 6 pi over 3. 2 pi. But I can recognize that I'm going to have to subtract a lot of circles to get down to a value on my unit circle that I recognize. So this is where you might think to yourself, should I subtract 6 pi over 3 at first? Or 12 pi over 3, that'd be 2 full circles. 18 pi over 3, 24 pi over 3 would be 4 full circles. 30 pi over 3. What if we subtracted 36 pi over 3? 6 full circles, that gets us to 4 pi over 3. And I do recognize that. 1 pi, 2 pi, 3 pi. 4 pi over 3 is right about here-ish. Say 30, 60, 90. Sine is the y value. It's going down a long way. So that's going to be negative root 3 over 2, if you remember special right triangles. Negative root 3 over 2. Cosine negative 990. So maybe I come over here to my calculator and I say, okay, well, negative 990, I know I need to add a full circle because I want to get back to my familiar positive values. Plus 360, I'm still negative. Plus 360, I'm still negative. Plus 360, oh, negative 990 is coterminal with just 90 degrees. And so 90 degrees is, well, it's right here. The cosine is the x, so what is my x coordinate? Just 0. Just 0. Because I added all those circles and found, okay, that's coterminal with 90 degrees. There we are. Last one, tangent of 7 pi over 2. Well, 7 pi over 2 minus 4 pi over 2. That's a full circle, that's 2 pi. Gives us 3 pi over 2. I do know where that is on my unit circle. 1 pi over 2, 2 pi over 2, 3 pi over 2 is right down here. Tangent is y over x, so negative 1 over 0. Undefined because we can't divide by 0. I said at the beginning of this video, this is kind of a unit circle type lesson, and it really comes down to your knowledge of the unit circle. So all the work that we've been doing, the little bits and pieces we've been adding on as we go, this is where it's starting to pay off because we know just immediately, oh, cosine negative 990. We'll add a few circles, that's 90 degrees. Cosine's the x coordinate, so 0, because it's right here, and there's no x coordinate. We didn't move out of the y-axis. I shouldn't say there's no x coordinate. The x coordinate is 0. So circular functions, talking about the period of these functions and talking about cosine is x, sine is y, and using the fact that we can add and subtract full circles to end up at the same spot and come to familiar values. That's what 13.6 is all about. So take a look at your practice problems. That's it for this video. Let me know what questions you have. We have one section left in this chapter, and that'll be covered in the next video, 13.7.